Welcome to this explainer. Today we're taking a massive leap. You know, the rapid evolution of modern web applications has fundamentally shifted how software engineers approach data. We're moving completely away from those old legacy client-driven pulling patterns, and we're entering this highly responsive era of event-driven pushing. To deliver true real-time capabilities, whether we're talking about live trading dashboards, collaborative editors, or automated cloud workflows, architects really have to navigate some incredibly complex choices. So, in this explainer, we're going to focus heavily on the introduction to these concepts, the underlying architecture, and, absolutely crucial, the developer perspective of these transport protocols.
Okay, let's dive into this. Here's the agenda we're looking at today. First, the real-time web evolution. 2, the architecture of webhooks. 3, the architecture of WebSockets. 4, the developer perspective. 5, future paradigms. And finally, number 6, the architectural decision matrix.
All right, part 1, the real-time web evolution, moving beyond legacy pulling.
So to really understand where we're going, we first have to look at the fundamental problem with legacy web communication. Traditional REST APIs, using your standard request-response model, they're perfectly optimized for transactional create, read, update, delete data operations. But here's the catch. They completely lack a mechanism for the server to initiate communication without an explicit client request. Forcing client-side polling to discover state changes? Well, it's literally like repeatedly driving to a physical post office just to check for new mail. You create massive network overhead and high server load, even when absolutely no state changes have happened. Event-driven pushing, on the other hand, is like having that mail delivered directly to your front door the absolute second it arrives. It's highly efficient, it's immediate, and it absolutely slashes unnecessary server load.
Moving on to part 2, the architecture of webhooks, ephemeral event push.
To overcome the glaring constraints of legacy polling, real-time web architectures rely on a few primary paradigms. Let's look at the architectural mechanics of our first solution, setting up webhooks as ephemeral HTTP callbacks. You'll often hear a webhook characterized as a reverse API. So instead of the consumer asking for updates, the producer automatically dispatches a payload to a pre-configured HTTP or HTTPS endpoint immediately when an event actually occurs. Because it operates statelessly at layer 7 of the OSI model, this connection is fundamentally ephemeral. It's there, and then it's gone. Let's quickly walk through the precise 3-step structural flow of a webhook transaction, just to really ground this architecture. Step 1 is the triggering event. This is a state change within the source provider, like, say, a payment clearing. Step 2 is the structured payload. That's a data packet, typically serialized in JSON, containing all the event details. And step 3 is the receiving endpoint. That's a public URL exposed by the destination application, designed exclusively to listen for incoming HTTP post requests. The moment the receiver processes that request and returns a 2xx HTTP status code, boom, that connection is immediately terminated.
Okay, part 3, the architecture of WebSockets, persistent full-duplex communication. Now, what if you need an ongoing conversation rather than just a one-off notification? First, we really need to clear up a common architectural error by highlighting the crucial distinction between raw network sockets and WebSockets. So raw sockets operate down at layer 4, TCP or UDP. They are abstract software endpoints running entirely outside the boundaries of web browsers, meaning browsers literally cannot natively open them due to strict security constraints. WebSockets, however, are standardized under RFC 6455. They're a layer 7 application layer protocol, fully integrated into almost all modern web browsers, and they're specifically designed to bring persistent, bidirectional communication straight to the web. Let's look at exactly how this builds into a persistent connection. A WebSocket connection actually begins its life as standard HTTP. The client sends an HTTP GET request with a specialized upgrade header. If the server accepts it, it returns an HTTP 101 switching protocols response. And once this handshake completes, the HTTP protocol is entirely discarded, the underlying TCP connection remains wide open, allowing both the client and the server to push text or binary frames back and forth asynchronously. It's a really elegant handoff. Now, what's really interesting about this slide is the rigorous data comparison regarding state and overhead. The differences are honestly stark. Webhooks are stateless and ephemeral, which makes them incredibly easy to scale, but they carry high framing overhead. We're talking hundreds of bytes of HTTP headers for every single delivery. WebSockets, conversely, have incredibly low framing overhead, literally just 2 to 14 bytes per frame header. But the major trade-off is that they are stateful. Keeping thousands of concurrent connections open requires significant, persistent server memory just to store session state and socket file descriptors. All right, moving to part 4, the developer perspective. Let's talk implementation realities.
With all that architectural theory established, let's look at the practical implementation realities and blueprints that engineers face every single day. So, the crucial point is that public webhooks are highly vulnerable to spoofing and chaotic network behavior. You absolutely must secure your endpoints by verifying HMAC signatures using SHA-256. This ensures the payload actually came from a trusted sender. Furthermore, because providers use an at-least-once delivery guarantee, you are going to get duplicate events. It's guaranteed. You have to implement idempotency logic, like, for example, using Redis to manage locks based on processed event IDs, just to prevent data corruption. Finally, developers must manage downstream resources via rate limiting and monitor strict structural platform limits. Like Stripe, for instance, restricts users to a maximum of 16 distinct active webhook endpoints per account.
On the flip side, WebSocket client resilience requires incredibly complex blueprints. Because these are long-lived connections, edge proxies like Nginx have to be explicitly configured to forward HTTP upgrades and use really long read timeouts. Developers have to implement ping-pong heartbeats to actively hunt down and eliminate dead zombie connections. And crucially, this is huge, you have to build robust client reconnection loops using exponential backoff combined with random jitter. If you don't add that random jitter, you risk the dreaded thundering herd problem, where thousands of disconnected clients retry connecting at the exact same millisecond and just instantly crash your server. No one wants that.
Let's move to part 5, future paradigms. We're looking at SSE and WebTransport.
Both webhooks and WebSockets have well-defined trade-offs, for sure, but the real-time ecosystem just continues to evolve. Many applications actually don't need a two-way street at all. They only require unidirectional server-to-client updates. In these specific scenarios, server-sent events, or SSE, have emerged as a highly efficient alternative to WebSockets. SSE operates straight over standard HTTP, simply keeping the response open to stream text-based events.
The resurgence of SSE is fascinating. Historically, back under HTTP/1.1, browsers strictly capped concurrent connections. But today, HTTP/2 multiplexing completely solves this. It allows up to 100 logical streams over a single TCP connection. SSE is brilliant because it includes built-in client reconnection handling right natively in the browser. It works flawlessly with standard caching layers, and it easily bypasses proxy firewalls. In fact, it has become the gold standard for large language model AI token streaming. It's utilized directly in the SDKs of major AI providers like OpenAI and Anthropic. It's a huge deal.
But what if you need bidirectional communication without the underlying limitations of TCP? Enter WebTransport. Built to run over HTTP3, which itself is built on UDP and QUIC, WebTransport represents the next major evolutionary step to solve massive latency bottlenecks associated with traditional WebSockets. And this brilliantly illustrates exactly how we overcome legacy networking limits. Because WebSockets run on TCP, if a single packet is lost, the operating system literally pauses the entire connection window until that specific packet is retransmitted. This is called head-of-line blocking, and it's a huge pain. WebTransport's TrueStream multiplexing completely resolves this. Furthermore, it enables unreliable datagram transmission for ultra-low latency needs, think gaming telemetry, and it features connection migration, allowing a session to survive seamlessly when a user switches, say, from their home Wi-Fi straight to cellular data without dropping a beat. Finally, Part 6, the architectural decision matrix. Let's talk strategic deployment.
With all these powerful tools on the table, from basic HTTP callbacks to advanced QUIC-based streaming, it's time to consolidate our understanding. Choosing the right real-time architecture requires selecting the exact proper tool for your specific communication scenario, right? So for decoupled server-to-server integrations triggered by distinct system events, stateless webhooks are your ideal choice. If you are building full-duplex interactive browser apps like collaborative editors, WebSockets remain the production standard. For unidirectional server-to-client streaming, especially AI tokens, deploys server-sent events. And for latency-sensitive raw telemetry operating on unreliable networks, you're going to want to look to the emerging hybrid implementations of WebTransport.
We've covered a tremendous amount of ground today, from the fundamentals of the real-time web evolution all the way to the bleeding edge of application layer protocols. The landscape is shifting dramatically under our feet. So I leave you with this final provocative thought. As web infrastructure matures into 2026 and 2027, how will the inevitable shift toward UDP-based protocols completely redefine the latency limits of your current stack? It's a thrilling time to be building on the web. Thank you so much for joining me for this explainer. Keep learning, keep iterating, and I'll catch you next time.